Okay, in this video I'm going to demonstrate how you can use the Stata graphical user interface in order to specify and test a path analytic model. So basically I'm going to demonstrate various features associated with the program and run a basic model and illustrate some of the where you can find some of the outputs associated with global model fit as well as model fit at the equation level. This is not to be intended to be an exhaustive video by any stretch, so it's necessarily going to be limited, but this is, like I said, an effort to give you sort of an overview or a bird's eye view of how you can use the program. So the first step that I'm going to demonstrate is just simply how to pull data, a raw data set, into the Stata program. And basically Stata, in order to run your analysis, you have to have a Stata data file. So if you have your data in a different file format, then you're going to need to import it into the program, save it as a Stata data file, and then run your analysis from that. If your data is already in a Stata data file, then you would not need to worry about this. You can just run the model straight from that particular data file. So just to illustrate the process of importing the data, I'm going to import some data from a Microsoft Excel file. What I'll do is I'm going to go to File, go to Import, and Excel Spreadsheet because my data is in this particular format. So I'm going to click on it and then go to Browse, and then here, this is where the actual raw data can be found in this particular file here. So at this point I'm going to click on Open, and you'll see that in row 1 I've got the variable names, and then below I have the values on those variables for each case. So I am actually going to click Import First Row as variable names so that the actual raw data starts right below here. So once I've done that, I'm going to click on OK, and so now you can see over here name and label. Basically the variables have been imported into Stata. We still have not saved it as a data file just yet, but we can look at our data. If we go to Data, Data Editor, we can go under the Browse mode, and you can see we have our variable names up here. We have our values for our variables down below. If we wanted to make any kind of changes or additions manually, we couldn't do that using this particular mode right here. We would actually have to utilize the edit mode to do that. So if we went to Data Editor and to Edit, we could theoretically change any values, or if we wanted to add in some cases, maybe some data was missing and we figured out what it was and we wanted to put it in, we could certainly do that. But nevertheless, we have our raw data, and the next thing I need to do is to actually save this as a Stata data file. So I'm going to click on Save As, and actually I'm just going to call this Path Model 3. And then you can see we have down here an extension, DTA, that's for data file. So we're going to click on Save. So now this file is saved, and so we can run our analyses from this particular data set. This data set that I have currently is a complete data set, but it only has 100 cases. So first of all, ordinarily you would not be running a path analysis with only 100 variables. Secondly, for the purposes of this video, we're not going to focus on data screening and dealing with missing data. That's a considerable topic all its own. So we're going to mainly focus, like I said, on specifying a model using these variables and testing it out. So at any rate, the data is now in. You can see that you have in the output file, you can see that all, basically what we've done, you have the command actually given associated with each thing that or rather each step that we've taken thus far. So Now what we're going to do is we're going to go to statistics and we'll go down to SEM, structural equation modeling, and we'll click on model building and estimation. And so here we have the graphical user interface, and we're going to specify our model. And we could theoretically specify our model using some basic syntax associated with the program, but in this case I'm just going to focus mainly, like I said, on drawing out our model and testing it using this interface. So over here on the left you'll see we've got boxes, ovals, and arrows, and even double-headed arrows, and some other variants as well. And so in traditional SEM notation, measured or variables or observed variables are indicated by boxes. We specify proposed causal associations using the arrows. So I'm going to lay out a basic model, and the way that I do this, these are little buttons over here. So I'm going to press this little button and basically move, draw out a box. I'm just going to put it right here. And you'll see that now, as long as this button's pressed, then I can basically continue to draw out these variables here. Once I click on this little icon here, that unhighlights this, and so now there are no more. I can't draw a box in that way. So I'm actually just going to continue to draw out my boxes. And then click on this little arrow. Next, I'm going to go up to Object and go to Properties. Actually, before I do that, I'm going to highlight a box because I want the variable name to appear in the box and the variable information to be associated with a given box. So I'm going to click on Object Properties, and the first variable that I'm going to use is this one right here, and then I'm going to click on OK. And so now you can see that box, the variable name appears. So I'm going to do this for each one of these. So this is a fairly simple process that we're working with. Okay, so at this point I've got the variables listed in the box, and the next step that I'm going to do is basically draw out the proposed causal associations. So I click on this little arrow button right here, and I'm going to draw out the path here, path here, all right, let me try this again. Draw our path here, and then a path here. And I'm just kind of drawing out some general proposed associations. So I'm not actually going to, this is not necessarily comporting with theory, but these are just some general, to give you a flavor of some of the general possibilities here. So you'll notice that as we draw out the arrows, what appears on what appears next to the each of our endogenous variables within the model are error terms. So basically, we think about these variables as not having any proposed causal variables associated with them. These are exogenous in the model. Variables that have other variables predicting the variance, these are basically referred to as endogenous. And so all endogenous variables will have a disturbance term associated with them. So that's basically unexplained variation or unexplained variance. I can also use the little double-headed arrow to specify covariances among these exogenous variables here. So there we go. All right, so now I'm going to click this little this arrow, so that, and then I click back on the screen, and so now we have a basic path model that has been specified. So the next step is to estimate the parameters within the model. So I'm going to go up to estimation and click on estimate, and you'll notice that the default method is maximum likelihood. If you had missing values, you could also click on maximum likelihood with missing values. If you wanted we're going to stick with maximum likelihood here. So if you look under this button right here, then you have different ways of estimating the standard errors for the parameters in your model. You can see that the default is, well, default standard errors, and that's one we're going to focus on. There's also robust standard errors. You can use bootstrapping and so forth as ways of estimating standard errors. But like I said, we're going to keep this video simple. So at this point, now what we're going to do is, if you look under reporting, you'll notice it says report p-values, test statistics, and confidence intervals. If we wanted to suppress those things, we could. I'm not going to. If we wanted standardized coefficients and values, we could certainly, in your display, we could do that, but I'm going to leave that off as well. So basically, at this point, I'm going to click on OK. And so now we have the parameters in the model have been estimated. So you'll see that this is basically an unstandardized solution, and these estimates actually appear back in the output file. So you can see that we've got our parameter estimates, the structural component. So we've got perceived threat going to dogmatism or dog. Certain and need for cognition going to dogma. And so these coefficients right here, you've got 0.05, 0.57, and negative 0.057. Those values are appearing here, here, and here. So these are unstandardized coefficients in the model. If I click on, so what you'll see is basically these are the paths, unstandardized path coefficients for each of the predictive relationships within the model. You have z values associated with each of those paths and a p-value that is given as well. So, and this is utilized in order to assess statistical significance associated with your paths. You also get a 95% confidence interval by default when you associated with each of the path coefficients as well. If we click on a given parameter within the model, let me kind of stretch this out just a bit. I want to give a little bit more room here. You'll see that what we end up with is we get over here, we get the regression coefficient, or excuse me, the path coefficient, the standard error, as well as the z value and the p value associated with it. So these are the same values that you see appearing in this part of the output file. Down below, you get the standardized path coefficients as well. So you would interpret this pretty much along the lines of a beta coefficient in regression. And it's also giving you standard errors and z values and p values as well. So, so basically, you would interpret this path coefficient up here. This is an unstandardized path coefficient that's appearing. Down below, this would be a standardized path coefficient. So you can utilize this information. Like I said, if you so you don't necessarily have to actually go right back to the original this output file here. You could actually just click on each parameter and you can get the unstandardized and standardized coefficients. Over here for the double-headed arrows, you get the covariance above because that's associated with the unstandardized solution, and down below this would be the correlation for a standardized solution. So at any rate, that's just a little bit about how you can look at the parameters individually within the model. And again, this is basically this piece of the output is just essentially going over, giving you the same information that we just saw within the path diagram. So the next thing I want to look at is the global fit of the model. So the way I can do that is if I go to estimation and then look at, and then basically go back to goodness of fit, and I can click on overall goodness of fit. And at this point, my recommendation is just go ahead and for statistics to be displayed, just click on all of the above and then on OK. And so now when we go to our output file, you can see we get the chi-square goodness of fit test, which is the same chi-square value that we see printed above, right below our table containing all our path coefficients. So basically what we're looking for is a chi-square test value that is not statistically significant. Basically, if the chi-square test is not statistically significant, that would be consistent with a good fitting model. Or in other words, the model fits the data pretty well. If it is statistically significant, then that would be indicative that the model is not necessarily fitting the data particularly well. So conventional significance level of 0.05 is oftentimes utilized. The downside of the chi-square test is that it is impacted by sample size, and given that path analysis and structural equation modeling procedures in general tend to be large sample techniques, it's not uncommon for the chi-square test to indicate that you have a bad fitting model or a poor fitting model because it's statistically significant. And so for that reason, it's also useful to look at other more descriptive indices in order to judge fit. By the same token, if you have a really low sample size, it's also possible that that this test would be non-significant, which would suggest good fit, even though there's more substantial departures from fit. So given that I have a sample size of 100 and I'm finding statistical significance here, I'm going to bet that we probably have a poor fitting model. But I'm going to look at some other indices. The RMSEA value, here it's 0.192. And basically, in terms of RMSEA values, the lower the better. As you get closer to 0, the more quote-unquote optimal the fit is. Less than 0.05 is definitely preferable. Less than 0.08 would be at least indicative of an acceptable fitting model. So you can see right here we're well above 0.08, and so the RMSEA value is indicating that we have a poor model fit to the data. If we go down below, we have the comparative fit index and the Tucker-Lewis index. Both of these values, we're looking for values that are above 0.9 or above, which would suggest a good model fit. And for both of these, that's not the case. These values are well below 0.9, and so this would suggest, these two indices would also suggest that we have poor model fit. Then down here we've got the standardized root mean squared residual, and so we're looking for values at 0.05 or below here, and so you can see we have a 0.084, which is higher than 0.05, and that would also suggest then that we have a poor fitting model. So just as a bit of a recap, a good fitting model will tend to have a non-significant chi-square value. In this case, we do have a significant chi-square value, which would suggest a poor fit. A good fitting model would have an RMSEA value, preferably below 0.05, but 0.08 or less would be considered acceptable. In this case, we have indication of poor model fit. When we look at the CFI and TLI, we're looking for values at 0.90 or above, and so in both of these cases, these values are below, which would suggest a poor model fit. And then for the standardized root mean squared residual, we're looking for values at 0.05 or below, and in this case, we have a value that is above 0.05, which would also suggest poor model fit. So in general, it looks like all of our indices are consistent with are suggesting that our model is a poor fit to the data. So we can also, if we go to estimation, we can, and goodness of fit, we can look at the equation level goodness of fit. So in other words, we're not just concerned with the overall fit of our model, but we're also curious about how well our predictors in the model explain variation in our endogenous variables. So when we click on equation level goodness of fit, I'm going to click on OK here because that's already set. And then when we look at our output file, you can see that we have R-squared values associated with each of our endogenous variables. So dogma, R-squared value is 0.35. So we would interpret that like we do in standard the R-squared value in multiple regression, which we would say that the predictors of dogma, which in this case were certain and need for cognition, basically accounted for about 35% of the variation in this variable. The predictors of perceived threat accounted for about 11% of the variation in that variable, and the predictors of aggressiveness accounted for about 31% of the variation. So basically, if you just multiply the R-squared value by 100%, you can discuss the variance accounted for in the endogenous variables in percentage terms. So next, I'm going to show you that if you go to estimation and then basically down to testing and confidence intervals, you can see that we can also ask for tests of direct and indirect effects. So I'm going to click on this really quickly here. And so we have a little table here. It says decomposition of effects into total, direct, and indirect effects. So, and you'll see that by default it says report p-values, test statistics, and confidence intervals. So I'm going to click on OK here and go to my output file. And so here it is. So, and actually I'm going to click on more because there's more to it in terms of the output. So up in the first table, you can see that we have direct effects. And so we have basically these are the direct effects that were specified in our model. So everywhere where we had a path laid out, these would all be considered direct effects. In terms of the indirect effects, these are basically testing mediated relationships between different variables. So you can see like perceived threat to dogma, there's no indirect effect because there's only a direct effect. If we want to talk about need for structure and aggressiveness, there are indirect effects to be had. So you can see that one indirect path or indirect relationship between need for structure and aggressiveness would flow through perceived threat. Another one would flow through perceived threat to dogma and then to aggressiveness. So basically, you can see right here, you got need for cognition to dogma. So need for cognition to dogma, there's a direct effect here, and then there's also an indirect effect through perceived threat. So basically, we have estimates right here of indirect effects as well as tests of their statistical significance. So right here we've got need for cognition to aggressiveness. If we wanted to compute this, basically this would just entail for the indirect effects, we would just basically take this path right here and flow through dogma. So there's one indirect effect. Then we have need for cognition through perceived threat to dogma to aggressiveness, and then we also have need for cognition to perceived threat to aggressiveness. So if we take take all that information together, then the indirect effect of need for cognition on aggressiveness within the model, we have a coefficient of negative 0.162. So basically, higher scores on the need for cognition would be associated with lower scores on aggressiveness. Is that indirect effect statistically significant? Well, we would look over here at the p-value for our test, and we can see it was statistically significant. So basically, oh, excuse me, that was the total effect. But actually, because there was no direct effect of need for cognition on aggressiveness, then the only effect of this variable on this variable is indirect. So essentially, so that's what this table of indirect effects is. So you can see that the coefficient here for need for cognition happens to be the same as it is for the total effects. But at any rate, this was, like I said, a very short and sweet overview. But basically, if you want tests of indirect effects, that's how you can ask for them. We could also, if we go to, if we want our estimates, if we just want standardized effects, we can click on Report Standardized Effects. And when we look at our output file, you can see that these are basically now reported in standardized terms. So you can see, like for instance, our indirect effect, or rather, you can see that basically we can get standardized output. So at any rate, the last thing that I want to mention is the test of modification indices. So let's say we want to see if we can modify the model in certain ways in order to improve model fit. There are various ways that you could do this. One strategy is to use modification indices, and so we can ask for those as well. And when we look at them, the modification indices, we can see suggestions in terms of proposed paths that might improve the fit. So here, the modification indices, one index is suggesting a path from need for structure to dogmatism. Another one is suggesting a path from dogmatism to perceived threat and certain to perceived threat. So let's say that I'm going to go with a bidirectional relationship. I'm going to add in a path here from dogmatism to perceived threat, and I can clean this up later. But basically, I'm going to re-estimate the model. So I'm going to go to Estimate and just leave all the defaults back on. And so there's our new model. It's been re-estimated here. And so, kind of clicking on these parameters here, you can see here's our unstandardized coefficient for the predictive relationship between dogmatism and perceived threat, and the standardized solution as well. If we want to look at, so again, here we have our output file with our path coefficients. If we want to look again at the overall goodness of fit of the model, we can go to goodness of fit. I'm going to look at overall and click on, leave it as all because we didn't change it. So I'm going to click on all. And you can see right here, in terms of the chi-square test, is still statistically significant with a p-value of 0.012. RMSEA value is still well above 0.08. The CFI now would be consistent with a good model fit, but the TLI, Tucker-Lewis index, is not. And the standardized root mean residual is below 0.05. So you have two indices that are kind of suggestive of good model fit, but you have basically the Tucker-Lewis, the RMSEA, and the chi-square test indicating poor fit. So I probably would not stick with this particular model. I might consider other modifications to improve the fit. If we want to look at the equation level goodness of fit, we can do that as well. So I'm going to click on OK. And now when we look at this, you can see we have the R-squared values associated with our variables. And so forth. So basically, that is in a nutshell some of the those are some of the features associated with the Stata graphical user interface and how you can go about running and testing a path model. So there's a lot more to it than this, but again, this was just to kind of provide a general overview.